Let's talk a little bit about filters and how they are related to transfer functions and Bode plots and the other topics that you're learning. So one thing a circuit can do is to allow certain frequencies to pass through and to filter out other frequencies. So when you have a circuit, you have an input and you have an output. And the output can depend on the frequency. So you will have frequencies that are allowed through, and those will be called pass band. And you have frequencies that are not allowed through, and those are called stop band. And one way that we study these is by looking at a frequency response plot. And an example of a frequency response plot is a Bode plot. And when you look at a frequency response plot, you'll look at both a magnitude plot and you might look at a phase angle plot as well. But let's look at these 4 different types of filters. So you have a low-pass filter, and what a low-pass filter does is it allows lower frequencies through, and it does not allow the higher frequencies through. So the little dotted line is the ideal low-pass filter. So an ideal low-pass filter lets the low frequencies in, and then at a certain level it stops and does not let the high frequencies in. Now, an actual filter will look something more like the blue line on there. So it allows more of the lower frequencies in and less of the higher frequencies. So then you also have a high pass filter, and the ideal one looks like this. So 0, the magnitude is 0 for the lower frequencies, and the magnitude is 1 scaled. So in other words, it lets them all in for the high frequencies. Then you have something called a band pass filter. Now, ideally, it's 0 until you get to a certain level, and then it lets them all through, and then you get to another level, and then it becomes 0 again. So that'd be an ideal band pass filter, but the actual band pass filter would look something like the blue line, and then you have the band reject filter. So the band reject filter will allow the low frequencies in, and then for a certain band of frequencies will not allow those in, and then as you get high enough, it will allow those in. So when we're talking about a low-pass filter or a high-pass filter, then you're talking about the frequencies at which it filters out. And there also is going to be a variation in the phases that also depends on the frequency. The circuits that we're looking at now are called passive filters. Passive filters, for the most part, will not have their output amplitude any greater than 1. So you're not really amplifying them, you're just modifying them somewhat. Passive filters contain only passive elements, such as resistors, capacitors, and inductors. So if you want a large amplitude, a large output amplitude filter, then you would have an active filter, and that's not what we're looking at right now, although you will look at those in electronics. Okay, so now let's take a look at a low-pass filter and how it works. And let's consider a simple RL circuit. Okay, so I have an inductor L, have a resistor R, and there is a voltage across this resistor, and that would be my output voltage. And let's think about how this filter would act at different frequencies. So let's start by saying low frequency. And when I'm saying frequency, I'm talking about angular frequency, but a low angular frequency is a low frequency as well. So a low frequency, as a matter of fact, let's let the frequency equal to 0. So what does it mean for the frequency to equal 0? Well, you studied all of those in circuits 1. When the frequency is equal to 0, that means you have DC. You don't have any oscillation. So if the frequency equals 0, then we're in a DC situation. And our inductor acts just as a straight wire. So frequency equals 0 gives us DC, and so that allows all of the magnitude, the complete signal will get through. So that's at low frequency. At high frequency, remember when a current just first starts flowing, the inductor acts as an open circuit. And so if you have very high frequency, then it's like the current is going back and forth and back and forth. And so it's constantly changing, and that is going to make this inductor act as a open circuit. So high frequency, then our magnitude equals 0, and here our magnitude, and this is just going to be the gain, so what you would multiply it by is 1. So a very simple low-pass filter is just an RL circuit. So an RL circuit is a low-pass filter. Okay, so now let's talk about what we mean by the cutoff frequency. So if it has some frequency that we're saying is where it cuts off, what is that frequency? So our cutoff frequency. And typically, the way the cutoff frequency is defined is it is the frequency at which the magnitude of our transfer function equals the maximum magnitude divided by the square root of 2. So this would be our cutoff frequency, omega c. Now let's consider why this might be a reasonable way to talk about the cutoff frequency, or a reasonable definition. So we know the definition of a transfer function tells us that the transfer function h of omega equals v out over vn. Now, let's say that we have maximum v out. So v out is as big as it can be. Well, if v out is as big as it can be, then h is also as big as it can be. So h max of omega equals v out max of omega over vn of omega. Now, when we're talking about maximum, then we have to be talking about the magnitude is what we're talking about, is the maximum. So we would say, we can have all of these be magnitudes. Now, we just said that h max over the square root of 2 is what we define as at the corner frequency. So the maximum h max will be the square root of 2 times the magnitude of h at the corner frequency, and that equals the magnitude of v out over vn at the corner frequency, or the cutoff frequency. So now we can say v out equals vn times the square root of 2 times the magnitude of h omega c. But we also know that this vn times h omega c gives us v out max from this equation right here. So vn times h max equals v out max. So in this instance, v out equals 1 over the square root of 2 v out max. So what I'm saying is, at the corner frequency, or cutoff frequency, our output voltage is our maximum voltage, maximum output voltage, divided by the square root of 2. Okay, well, we know that our real power in an AC circuit is 1/2 the magnitude of the voltage squared divided by the resistance. So at the cutoff frequency, the power will equal 1/2 V out max over the square root of 2 squared over R. What is this? This is 1/2 V out max squared over 2 all over R, or 1/2 times 1/2 V out max squared over R. This would be our maximum power. You'll have maximum power, we have maximum voltage. So our value of our power at our cutoff frequency is 1/2 the maximum power. So the power at omega C is 1/2 the max power. So that gives us another kind of motivation as to why making the cutoff frequency be the frequency where the magnitude is the max magnitude over the square root of 2 makes sense, because that is where your power is half of your maximum power. And I think I will stop here, and the next video I will do some theoretical justification for why we are doing everything we're doing with these transfer functions.